Hello, I'm Chuck Hurstis, a senior consultant here at the End User Compute Center of Excellence for VMware, and today I'm going to share some guidance on Piece-over-IP optimization and tuning best practices. So first, I'll give a brief background of the protocol, and then follow that up with a rundown of some key features. As the Piece-over-IP feature set and number of client endpoints supported has grown, we're now at a point where I'll discuss a client compatibility matrix as well. And then we'll move into tuning PC-over-IP. This is broken into three major sections: network deployment best practices, an overview of the tunable parameters within PC-over-IP, and the last section which goes into some guidance on how to apply those parameters to specific situations. Finally, I'll share a few links to additional information regarding the optimization of PC-over-IP. First, a little background. So PC-over-IP is a real-time protocol. I'll be saying that a lot because I think it's an important point to understand. I consider any protocol that has a very high requirement for user responsiveness and that may require special classification on the network to be a real-time protocol. That's a pretty broad and generic definition, but I think few people would argue that user experience or desktop responsiveness in a VDI environment is every bit as important as VoIP or telepresence responsiveness, and those are considered real-time protocols. So, why not PC over IP? PC over IP is also host encoded. This means that all the image updates are rendered on the host side and then encoded for transmission. No application drawing commands or other low-level interaction with the desktop is remoted to the client. So, from the virtual desktop point of view, everything renders locally. And this allows for very fast application rendering and response because the applications aren't waiting for the client side to do any work. It also allows for greatly simplified endpoints. A simple way to look at it is that PC over IP scrapes the screen on the desktop side and then encodes it in real time, almost like a media stream. Endpoints then only need to be able to decode that stream to be able to display it. And this avoids tying the endpoints or the virtual desktop itself to any current or future desktop OS technologies. And it allows for immediate compatibility with whatever the next big thing is. So as long as the desktop VM can render it, a PC over IP client can then display it. And then lastly, it's important to note that PC over IP is UDP based. So this makes sense for a real-time protocol. It avoids a lot of the TCP overhead and processing that might slow down or otherwise impact the user experience. So PC over IP implements reliability at the application layer because only PC over IP can know what data is valid or what data can safely be discarded if it failed to arrive. UDP is a stateless connection, and sometimes packets don't make it across. Now, in the case of full motion video, if that data has already been replaced on the screen, there's no reason to try and resend it. Now, if you let the network stack make that decision, as you would in a TCP-based protocol, that implementation can be pretty inefficient, and you're going to resend a lot of data that may be meaningless by the time it arrives. So let's focus on a few key features of the PCoIP protocol. This is not an exhaustive list by any means, but a few highlights that I think are relevant to this session or that have been recently added or updated. So I wanted to point them out. And the first is build to lossless. Sometimes you'll see this called progressive build, and all it really means is that PC can utilize lower quality updates on portions of the screen that are in motion and then rapidly build them to pixel perfect once they become static. So, for example, scrolling a document or even a flash banner ad in a web page, while that content is in motion, most people will not notice that it's been slightly degraded in quality. And we get significant bandwidth savings by not having to send full fidelity images of the content during that time. Once things become static, so when you stop scrolling, PC over IP will render to fully pixel perfect. Unless, of course, you have disabled build to lossless, which is a new feature, and are only building to perceptually lossless. So that's a recent addition, and it allows you to further reduce the bandwidth by rendering to a point where the screen, while it's not pixel perfect, is just about indistinguishable, hence the perceptually lossless. We perceive it to be pixel perfect, though it technically is not. Image decomposition is the next feature I'll talk about, and that's a means to optimize bandwidth yet again by applying the right kind of codec and compression to different types of screen content. So, for example, while text has to be preserved in a lossless format, you wouldn't want to do that for full motion video or even when you're scrolling a page, as I talked about earlier. Um, some kind of a lossy codec is going to be a better fit for that content. And I'll talk a little bit more about the recent updates to the text codec later on. But for now, just understand that PCoIP analyzes the content on screen and then applies the optimal codec for the specific content found in any given region. So it encodes and compresses text one way, video another way, icons another way, photographic images, yet another way, and it'll choose the most optimal codec for each of those types. Next, PCoIP is an adaptive protocol. So when bandwidth is available, PCoIP will use as much as it can get. And that's to ensure that end users get the best experience. If the bandwidth is there, why not use it? If it means that the end user gets a more responsive desktop. But when network conditions change, PCoIP will automatically adapt down and throttle itself back to avoid overrunning whatever of bandwidth is available. Or maybe it's a latency or a congestion that have spiked up. So PCoIP will detect that and throttle itself down. So later on, we'll see how we can put some bounds around this behavior and control it a little bit more. But even then, PCoIP is always measuring network conditions and trying to provide the best experience possible within the bounds we give it. Client-side caching is another bandwidth-saving feature. And simply put, this is the ability to store frequently accessed static content, and that's important, on the client endpoint device and then present it back to the end user without requiring that data to be sent across the network again. So I'll speak to this in a bit more detail, so I won't cover it very much here, but we'll see more on that shortly in a few slides. The last feature I'll talk about here is the WMI session monitoring. So this lets you see in real time how the PCoIP session is behaving, how much bandwidth is being consumed, network quality, and several other counters. And again, this is one of those ones where I'll go over it in a bit more depth once we move forward a little bit. So as I stated previously, let's take a closer look at some of the new features. In this case, those that directly affect bandwidth consumption are the ones I'm going to focus on. I talked about image decomposition previously and mentioned that using different codecs for different types of content is an effective way to save bandwidth. Well, I want to take a moment here and call out the text codec specifically, as it's been recently updated to provide a 2x increase in compression ratio versus the older versions of PCoIP, while still providing lossless transmission of text. So since very few pages are just purely top to bottom text, or very little screen interaction that an end user might do is just completely nothing on the screen but text, you don't get a 2x saving in bandwidth, but you do get about a 10 to 20%. So still a significant savings, and retaining that lossless quality of the text. I also spoke about build to lossless and a new mode where you can build to perceptually lossless. As you can hopefully see in the image, I hope it's clear on this recording, the difference between pixel perfect rendering and perceptually lossless rendering is pretty much unnoticeable with the human eye. It can be measured qualitatively by a computer program analyzing a pixel perfect image and a perceptually lossless image, but for most people, you're not going to notice the difference. The good news with this is that makes it applicable in just about every use case where PCoIP is going to be deployed. There are a few use cases where it's critical to have that pixel perfect display, medical imaging, CAD CAM, very high-end digital graphic design as well. And in those cases, you want to leave that option off and render to fully lossless. But you can expect to see about another 10 to 15% reduction in bandwidth with a perceptually lossless image versus a fully lossless image. So, you'll see later the advice on this is, pretty much turn it on. It's a no-brainer. Because for most use cases, no one's going to notice. And then lastly, a little more detail on client-side caching. This is where you have a client resident cache that stores static content. And that's important because it doesn't do full motion video or any other content that's moving around. Essentially, it makes no sense to cache that. You can't capture an image of that content. But any content that's static will be stored to the cache. That data or that image data is then presented locally from the cache rather than sending it across the wire again from the server side. So Instead of sending that image data, PCoIP just sends an address into the cache and then the location of where to display that content. And that's a bit oversimplified, but it covers the basic premise. So this feature, when used on a supported device, can show pretty significant gains in bandwidth reduction, as high as 30 to 40% for some use cases. So here's an example of a full screen looping slideshow. And this is a bit of an idealized case, I admit, but it's not unrealistic. If you imagine a thin client providing digital signage at a retailer, or maybe a remote kiosk with an attract loop, where it just rotates frames every 20 seconds or 15 seconds, both of those are practical manifestations of this simulation. So while I sped this up for the sake of just being able to measure it more quickly, the use case itself is still actually valid in the real world. In this case, the frames were flipping at 1 update per second, so it's almost more like a movie than a slideshow. Hence, you see that really big spike of bandwidth at the beginning. But what you see is, after that initial content load, bandwidth drops off substantially. And if you look in the bottom, which is really just a zoomed in representation of the same graph, you can see that to present that same content that peaked as high as 4.5 megabit, obviously, remember, we're completely refreshing the whole screen once a second with photorealistic imagery. That's a pretty big spike, but then you come down to using just over 50K to present it after the fact. So client-side caching can be very, very effective for certain use cases. Now I want to give a practical example on a desktop. In this case, it's more of a visual example than measuring bandwidth. When you look at this, you can see it's just a static, basic desktop, and the grid that's overlaid is showing the areas of the screen that have been cached. So as you can see, just about the entire desktop can be served up from cache here. It's already in there. The grid overlays essentially the entire image. So let me open a document here. This is a PDF. And what you'll see is that pretty much immediately, the gray areas to the left and right have been cached. The same with portions of the title bar. You can see the grid overlaying those areas. But none of the graphical images are in the cache outside of the pure black areas, which were reused from the black desktop, right? So the client-side cache is smart enough to know that content within the cache can be repeated and layered. So, there's one black tile, and that's repeated and automatically pulled from cache anywhere that tile will match the content on screen. It doesn't matter that it's on the desktop or within a document. So that makes very efficient use of the cache. So in this case, notice one other thing I'll point out is that you can notice that the text isn't cached either. So the graphical images are not cached and the text is not cached. Now, after scrolling this document or this page off the screen and then scrolling back up, you'll see that in this representation, pretty much all of the graphical images were served up from cache and all the text as well. So in addition to everything else, the gray and the title bar and everything else that was already cached pretty much immediately. So what this means is that scrolling off did consume bandwidth because the content had to get there, but scrolling back up into this page used almost no bandwidth at all. It was very little, similar to the previous example of 50K, 60K, to be able to render that content because it came completely from cache. So let's talk about visibility and monitoring. And this is really just drawing out a little bit of information on those WMI session counters. They do give you real-time visibility. There's 30 plus stats, and they're broken into 5 general categories. General, which is basic things like the total session duration and the overall number of bytes transmitted received. Network-specific statistics, such as bandwidth transmitted received for individual portions of the stream, and latency and packet loss. Imaging data, so specifically the imaging bandwidth sent and things like the image quality and frames per second. And then similar settings for audio and USB, so bandwidth and quality settings for both of those. Now, to get at these stats, you will need some kind of a tool. So all of the third-party tools, the big names, Lakeside, Liquidware, Zangati, and many others, have announced support for these WMI counters in their products. So you can plug them into your view environment and get those, but there's always free options as well. And Windows PerfMon is pretty much ubiquitous. It can monitor these stats remotely with correct configuration. And admittedly, this is a shameless plug, but the PCoIP log viewer, which is a tool that I have released, can also connect remotely in an agentless fashion and then pull these stats. And I'm hoping to get that out as a fling within a while, but I'll have information and links for how to get that tool at the end of the presentation. So let's talk about that client compatibility matrix. I mentioned a couple times, this or that when using a supported device. So in this case, because the feature set has changed, focusing on those three bandwidth saving features, you can see that all the soft clients, Windows, Mac, and Linux, do support all three. So you can expect to see pretty significant bandwidth gains, bandwidth reduction there. The mobile clients, so iOS and Android, do not support the client-side cache, but they do support the text codec and disabling build to lossless. So you'll see some savings there as well. We talk about zero clients. We do get the build to lossless savings on those. And then we talk about future zero clients coming, and I believe these will be out in 2012. Those will have full support. So you'll be able to reap all the benefits of those bandwidth reduction features. I think this is important to know as people are selecting client types when you're doing a POC or a pilot. Things are changing, right? Features are being added, and client compatibility can be a very real issue. So let's move into tuning PCoIP. And these are really network best practices, and this advice hasn't changed in quite some time, so I'm going to go through it fairly quickly because I think it's been put out many times, so there's not a lot of new information here. I've said this before, PCoIP is a real-time protocol, so ensure that there's proper quality of service class of service classification. You want to get PCoIP traffic above all other TCP and non-real-time traffic, but probably below VoIP. And this is going to vary. There's no one way to do this, so unfortunately I can't give you the exact markings that'll work in all situations. Different network teams do this in different ways. But what's important is that PCoIP is not thrown into the scavenger queue with all other non-critical traffic. Treat it like a real-time protocol. Utilize the View security server for remote access. It really is the most efficient way. It's entirely UDP-based. It almost acts like a reverse proxy in the way it works, but it guarantees that you're not going to have any additional overhead or complexity when your users want to get remote access. Another interesting benefit of this is that it actually allows zero clients to have remote access, so you don't have to have a VPN for those. So this is really good for work-at-home use cases where you want to have the simplest and easiest to maintain endpoint, but you still need to give people remote access. The security server will do that. If you can't use the security server and you have to use VPN, avoid SSL-based solutions. So don't use the SSL mode of the VPN if it supports other modes. You want to use IPsec, LTTP, IPsec, really the same thing, GRE, DTLS, or there are a few other implementations that will allow UDP tunneling and not UDP encapsulation. When you encapsulate UDP packets in TCP and have them travel a TCP SSL-based VPN, you lose all those benefits of being a UDP-based protocol that I spoke about earlier, and you're subject to the conditions of the network. So if there's any loss or any drop packets, the end-user experience degrades significantly and very quickly. PCoIP does not benefit currently from WAN optimization, so you want to bypass it on WAN acceleration devices. It can still pass through the device, but don't have it being actively inspected or accelerated. It's just going to burn CPU time on the WAN accelerator device, and it's going to delay those PCoIP packets. There's really nothing that a WAN accelerator is going to add to the compression that's already there, and the PCoIP payload in each packet is encrypted. So they can't crack it open and do any more compression or anything else because it's already encrypted inside the packet. For that same reason, ensure that it's bypassed on IDS, IPS devices in the network path or on the endpoint protection software. So on the client, you also want to get rid of it. Prefer fixed bandwidth WAN circuits over burstable circuits, but make sure you understand your use case well, because you have to perform accurate measurements to allow for proper circuit sizing. You don't want to be too far over because that's very expensive. You don't want to be too far under because that's going to ensure a poor user experience. If you have to use burstable circuits, you have to ensure that the CIR is high enough to cover all of the existing high priority traffic and the total average traffic for the PCOIP session. So what does that mean? Most of the time when people get burstable circuits, it's because they know they only have a small amount of data that they consider critical, whether it's VoIP or telepresence or whatever that may be. That might be 6 megabit of traffic. So they'll buy a 6 megabit CIR and maybe a 30 or 35 megabit burst. And they put all other traffic in the burst, assuming they're using the full 6 megabit for VoIP and telepresence. That's great because the VoIP and telepresence traffic is guaranteed. The QoS markings will be honored, and it will traverse the network at appropriately high level of classification and priority. All other traffic is subject to being dropped because it's in the burst. If you don't grow the CIR at least some to allow the steady state average bandwidth of the PCoIP users you're doing, you risk having all of your users' desktop traffic classified as out of contract. And when PCoIP bursts, the carrier may just drop that traffic. Depending on other conditions, nothing in the burst is guaranteed. So it's very important to make sure that you verify that there's either enough room in the CIR existing to accommodate this traffic and classify PCoIP appropriately so that it rides in that stream, or that you buy more CIR to cover it. Now, you don't have to completely buy, if you had a 30 megabit burst, you don't have to buy 30 megabit, but you do need to do your homework and size it appropriately for the average bandwidth. For congestion avoidance, you want to use WRED, avoid tail drop. I believe tail drop is the default on many Cisco devices. There's a little bit of changing guidance around this, but generally I believe this advice still holds true. So WRED is just a more fair congestion avoidance mechanism. It doesn't, tail drop will just blindly drop all traffic until the congestion goes away. WRED will wait and randomize what packets get dropped, and it will also honor prioritization. So if you classify traffic as high priority, it will drop that traffic less than lower priority traffic. This generally allows PCoIP time to react and scale itself down. Lastly, this is just kind of common sense. Avoid use cases where round-trip latency is greater than 300 milliseconds. VMware and Teradici support up to 250 milliseconds of latency on paper, but I do know of cases that have gone, slightly beyond that, 260, 270, 280. But 300 milliseconds is sort of the great equalizer. So if you have a use case beyond that, you really need to carefully consider whether or not it's doable and if the user experience is going to be viable for the people on the other end. Generally, my advice is avoid those. Do not use per packet load balancing. This will cause out-of-order packet delivery because the PCoIP packets within a given session could be traversing two separate network paths, and those paths may have different properties such as latency and bandwidth, which will affect the timing and arrival of those packets. You have to really have session and stickiness or affinity turned on. So it's not that you can't spray PCoIP sessions over two network paths, but any given session should traverse the same network path for all packets. You don't want packet switching or load balancing to be going on within a given session, because PCoIP will tag any of those out-of-order packets as lost, in PCoIP speak, not physical network loss, and it will suddenly start to adapt down because it believes network conditions are very bad. Even if there's plenty of bandwidth available and latency is low, high packet loss will trigger PCoIP to throttle back. So avoid that. Use affinity or session stickiness, and all will be well. And then lastly, this isn't a network tweak, but just a best practice for deploying PCoIP, use the desktop VM optimization guides and configure the visual settings. Essentially, this means configure them down, right? Turn off a lot of the animations and fades and shadows on menus. Don't use the arrow themes and Chrome and all that stuff, because generally this just makes it easier to render the desktop. It's far easier to render a static menu than one that fades in. Fading it in is, will be treated like it's a full motion video. It's essentially animated, and that's going to consume significantly more bandwidth on average than just popping out a menu and popping it back. Because remember, we have client-side caching, so when that menu pops on, it will be cached. the next time it appears, as long as it pops on the screen as static content, it'll be served entirely from the cache. So you're going to get dramatic savings there. If it's an animation, as I said before, only static images can be cached. If it's an animated menu or fade in or fade out, that content won't be cached. So it'll have to be sent across the wire every time. And then lastly, we want to optimize the tunable parameters for every given use case. And that's what we're going to move into next, surprisingly. To get to the tunable parameters, you can either get to them via GPO, and this is within the PCoIP.adm file, and this is located on any connection server. So the path is listed there. You can find those files and then import it into your Active Directory controller, and you'll be able to set policy on your desktops. You can also set these values directly within the registry at the path listed here, that HK local machine path. So you don't have to do it via GPO, and in fact, in some cases, you can override GPO with local registry settings if that makes sense if you're testing new settings. I'm going to call out a couple of parameters specifically here because they are newer, and build to lossless is one of those. This is the ability to turn off full build to lossless, pixel perfect, and render to perceptually lossless. So you can see the GPO setting, and then that PCoIP.enable build to lossless is the registry key. So you put that in that path that was listed on the previous slide if you want to set this. Now, this one is a little bit confusing. I find the wording of it to be confusing. You're enabling this GPO setting to disable a feature. And more confusingly, the registry key is worded in the positive. It's worded as enabling build to lossless. So you actually have to disable in the registry key. So you want to put a 0 if you're setting the registry key, or a 1 to re-enable build to lossless. You want to enable the turning off of build to lossless via the GPO. And you also have to accept, there's a checkbox at the bottom here that basically states you know what you're doing, right? That you understand that you're going to be less than a pixel perfect experience, and there are potentially implications of that. So you have to accept that checkbox. If you just hit enabled on the GPO and hit OK without checking that box, it will not be applied via the GPO. Obviously, the registry setting, if you set it directly, you don't have to worry about that. But I do find this one, the wording of this one, a little bit confusing, and I know some people have been confused by it. Client-side cache, there isn't a toggle on or off, but you can control the size. And this may be useful. I'll get into a little bit of guidance on this later where this might be useful. But the default is 250 megabytes. That's usually safe. I think you can bump it up to 300 if you want, or you can bump it down to 50, and it goes in increments of 50 megabytes. If you set it via the registry key, I think you can set whatever size you like, and it'll be honored. So those I'm going to call out specifically. Those are two very recent additions. The rest of these I'll go through quickly, and I've subdivided them into a handful of categories. PCoIP network parameters. These control things like the overall max link rate, and this is that hard cap on how much bandwidth PCoIP is allowed to use for any one session. You can also set the session floor. So this is a lower bound. It isn't the least amount of bandwidth PCoIP will use. It's how far back PCoIP will throttle itself when it needs to use a lot of bandwidth. But conditions on the network do not allow it to peak at the amount of bandwidth it needs to do. So when it throttles back, it won't go below the floor if you set the floor. But never fear, if it needs 0 bandwidth because the screen is completely static, it will still continue to use 0 bandwidth. The floor doesn't set that value. MTU is another one. It's not really a tuning parameter, but if you are using many layers of encapsulation with PCoIP, coming through a VPN, and depending on the MTU size of the network, if you start to see packet fragmentation, that will be very bad for performance. So adjust the MTU, obviously reduce it if you are seeing poor performance and packet fragmentation, and that should clear it up. The next grouping is image quality levels. So minimum image quality. This is the lower bounds of the amount of compression that PCoIP will apply when it is adapting down to network conditions. So how low will you let it go? It defaults to 50%. It's usually a good place to leave it. Maximum initial image quality. This is a little bit harder to explain. It is when an image update is required, so when the screen changes, the first image update that is sent from PCoIP, this is setting the quality of that update. So the higher this value, the closer to pixel perfect that initial image will be. The lower this value, the more compressed that image will be. Setting it lower saves bandwidth. Setting it higher gives you higher image fidelity, but is going to make the protocol more peaky. And we'll get into some guidance on that a little bit later. And then obviously maximum frame rate. And this is just the number of updates per second that PCoIP is going to try and send. Lowering frame rate will reduce bandwidth, but obviously if you go low enough, it will affect the image quality. Videos will be jerky, but there's significant bandwidth savings to be done with this. And if you don't have video in a use case, you can go quite low with frame rate. And then audio parameters. The first option will completely enable or disable audio. So if you have a use case where audio is not required, it's probably safest just to disable it outright, and then you never have to fear that any bandwidth will be consumed by audio. If you do have to have audio, you can set a limit on that. And the second setting, we'll call that out. The default is 500 kilobits per second, which is actually rather high. So I definitely recommend if you have to provide audio, that you tune that setting out of the gate and reduce that quality. So let's move into some tuning guidelines. When should you tune? Cover all the best practices first. Obviously, confirm the network environment is properly configured. Go through all of those best practices I described previously. And confirm that you've done desktop image optimizations, because generally those two things are going to have a bigger bang for the buck than the tuning we're going to do here. Tuning a desktop that's on a poorly performing network with significant packet loss for PCoIP, or where PCoIP isn't classified properly, isn't going to have much impact. You have to make sure that PCoIP is on a healthy environment, and then you can fine tune it for a given user experience. So also remember that PCoIP already adapts. Sometimes you can be setting parameters and you won't see any effect, and that's because PCoIP itself is already dropping a value lower than your setting. So you're not having any benefit if it's already dropped the image quality because it's detecting packet loss in the network, and it's dropped the image quality to 70. Setting the image quality to 80 isn't going to have any impact. So remember that PCoIP is already doing some tuning by itself. And then remember that you can't get something for nothing. And I refer to tuning as an art because you're trading off bandwidth consumption for user experience and visual fidelity and quality. And there is an impact to this. And again, this may be hard to see in this presentation, but the out-of-box settings actually give a very high-quality experience. This is a still taken from a live-action video with two different tunings applied. And in the first one, you can see very minor compression artifacts. Those may just actually be compression artifacts in the source video itself. But on the right-hand side, you see major compression artifacts. So this is where we've really pretty aggressively limited PCoIP, dropped the frame rate, dropped the image quality. And you can see that same night sky is smeared and blurry. Now, in a video, full motion video, moving at 15 frames per second, or 12 frames per second, this may not matter. You may not notice those compression artifacts because the screen is always in motion. But this just goes to show that there is an impact. I mean, quality is reduced. You can't use less bandwidth and achieve better quality at the same time. If that was possible, we'd do it right out of the gate. So the art of tuning is finding that point where you've achieved maximum bandwidth savings, but impacted the user experience and the image quality as little as possible. So basic guidelines. Disable build to lossless. Really, it's the easiest way to just get a great benefit of bandwidth savings for most use cases. Again, as I said before, there are some use cases where you absolutely must have this on. But for everyone else, if it's not required, go ahead and turn it off and use that perceptually lossless. There's really almost no visual impact, but the bandwidth savings are very tangible. Also, configure the maximum session bandwidth. So more so for low bandwidth links, PCoIP will measure and it will determine if you're on a 5 megabit link that there's only 5 megabit of bandwidth, and it will throttle itself down to that. But if you already know that, you might as well give it an envelope to work in. Plus, if you let it just self-detect, it will still assume that out of that 5 megabit of bandwidth, it could potentially use all of it at any given time. Now, that may be fine, but you may want to reserve some of that link for other traffic. So you might want to set the cap at 4 megabit or 4.5 for any one session so that no one user can consume everything on that pipe. There's at least a little bit of bandwidth available for everyone else. And even on the LAN, it may make sense to set a limit on this, especially where you're doing a lot of high bandwidth user sessions concurrently. They can actually saturate and overrun the network uplinks. So no one individual user will kill it, but as a group, 200 or 300 users can actually saturate, a 1 or a 2 gigabit uplink. So it may still make sense to limit bandwidth even when you're on the LAN. Configure the session floor. When PCoIP is seeing a lot of packet loss and is adjusting down, but you've confirmed and verified that the network link has plenty of headroom. This is usually seen on a Wi-Fi access point or maybe a 3G or 4G connection because those can be very peaky and spotty, and PCoIP may throttle down on those. But if you know you have bandwidth, especially on like a 4G network, you can set the floor to keep PCoIP from being so aggressive. And this is just sort of forcing packets through the connection at a higher bandwidth. But there are cases where this does improve user experience. Now, be careful, because where you set that floor is as low as PCoIP is going to go. So you may unintentionally oversaturate a link because you've set the floor too high and you have too many users simultaneously trying to peak and then falling back to the floor where they would go lower if you hadn't set that value. They may consume more bandwidth, and that may unintentionally saturate the link. Configuring the maximum frame rate. I think this is something you can do in almost all cases. You probably don't need 30 frames per second at all times for most users. So this can easily be reduced to 18 or 20 frames per second, but you're probably not going to see a big bandwidth gain there because most users, especially task workers, and even generally knowledge workers who don't really watch a lot of video or multimedia, their average frame rate is significantly below 18. You can see there's a log file dump here, and those last 2 columns show the frame rate. So you can look in a log file, you can use the WMI image stats, frames per second is in there, and you can monitor this. So get a user on there, let them work for a day or two, see what their average and peak frame rate is, and then tune to that. If they're only ever hitting 5 or 6 frames per second on average, then leaving the frames per second set at 15 isn't going to have any impact. If they occasionally peak above 15, you'll shave off bandwidth there, but in the general use case, you won't save anything. You're probably better off if they're averaging 5 or 6 frames per second to set a cap at 6, right at the limit of that, where it's not going to impact 95% of what they do, but it's going to shave bandwidth off all those other use cases. But as with anything, 6 may be too aggressive. The users may notice that. So that's where that art comes in. Maybe 8 is a better value. But bear in mind that the higher you set that frame rate, the less of a bandwidth benefit you're going to get from this setting. So let's move on. Configuring the maximum initial image quality. When you're on a WAN link, honestly, maybe even on a LAN, I think this is pretty common. Reduce that setting to 60 or 70%, and I would recommend starting with 70. Especially for use cases that have large amounts of multimedia, so anything that's in motion, because each of those frame updates will now arrive at the lower quality setting, which saves a lot of bandwidth per frame. If you go too low with this, and you have a slow network link where it cannot rapidly build to either perceptually lossless or pixel perfect, fully lossless, users may notice that things are fuzzy or blurry because they're seeing those low bandwidth images for longer than they should. Things should build within a few milliseconds, so usually has very low impact. If it's taking more than that, you're probably going to have users complaining, and you may have to tweak this setting. Minimum image quality, the only thing that's important here is that it's below the maximum. So the default value of 50 is pretty much acceptable for most use cases. If you have to go to 50% on maximum initial image quality, you'll have to drop this below. So you might want to go to 40, but that's a pretty severe use case when you have to go that low. Configuring the audio bandwidth limit. So again, this is where you can't just turn audio off. You must have audio on, and you want to try and reduce the bandwidth it's using. And there are use cases where this is valid, such as legal transcription or medical transcription. bear in mind a few things about this, though. It's a target. It's not a literal value. So if you take it from 500K to 400K, it doesn't mean you're going to get 400K. You're essentially going to push the audio encoding to the next level of codec that's supported. So my advice on this is out of the gate, if you need audio but it's not critical, set this value to 100 kilobits per second. And I think that should get you about an average of 90 kilobits in bandwidth, which is 1/5 the default. So it's a really significant savings right out of the gate. The default of 500K gets you very high quality audio, but it consumes a lot of bandwidth to do that. And then obviously you can tweak it within that range. So maybe you can go below 100 kilobits. Maybe you need to be above that. But you do have a range. But just remember, it's not going to go exactly to what you set. So you might go from 100 to 110 kilobits, and you won't see any change until you hit 150, because that's the next tier of audio codec that's supported. And then configuring the client-side cache. This isn't so much a tuning or optimization factor. It's almost more diagnostic. On some thin client devices, they have limited RAM. And when you're using that 250 megabyte cache size, there may not be enough RAM on the client device to support a cache that large. So what you'll see is the desktop connects. It shows that it's logging the user in, and then at the point where the desktop itself would launch, the screen will go black and the client will disconnect. And that's because essentially the view client crashes on the thin client device. So you can go in with that GPO or that registry setting and reduce the cache size. Usually 100 megabytes or 50 megabytes has worked. And this is on a 512 megabyte client device where RAM is really limited once you have the OS loaded. Obviously, the cache will be less effective because it's smaller, but you still get benefits from it. And having a less effective cache is certainly better than having the inability to connect to a desktop at all. So this is a reasonable trade-off, but it may be something where you have to tune that setting. So in conclusion, right, always start with the basics before resorting to tuning the protocol itself. Make sure the network is tuned, make sure the image is optimized, right? Most of the PCoIP issues that people see with bandwidth have nothing to do with PCoIP. I shouldn't say bandwidth, but poor performance of the protocol have nothing to do with PCoIP itself and everything with the environment that it's running in. Make sure that you've properly sized the network. I mean, bandwidth, it is what it is. If you see the desktop and it requires 110 kilobits per second average bandwidth, then make sure you size to that. Don't just try and hit a number that's less than that, because you will pay for it in the end. Utilize the information in the logs and now the real-time WMI counters to determine where the trouble spots are. So where can you tune? Is image quality, maximum initial image quality very high? Can you drop that down? Is frame rate still at 30? Can you drop that down? And where should you drop it to? The logs will tell you that, and the WMI counters will also tell you how you should tweak those values. Always remember, right, vary one item at a time if possible. So you want to make sure you're moving in the right direction. So drop frame rate and then drop image quality. And you also want to be able to get user reaction to those, because sometimes people will respond better to a frame rate drop versus an image quality drop, depending on the use case. And the bandwidth settings may be the same, or bandwidth savings, may be the same. But user experience, if you chose to go the opposite route, you wouldn't be saving any more bandwidth, but the users would be more unhappy. So make sure you vary one element at a time, have a user test it, so that you can really get to that art piece of the tuning, which is saving that bandwidth, but keeping users happy. And honestly, if all else fails, reach out to VMware or Teradici for help. We've got a lot of experience doing this, and we're always happy to help. So additional resources, I talked about this earlier. Here are some guides. VMware View 5.0 Performance and Best Practices Guide is a really good write-up, a very recent white paper that was released, and has some good tuning advice in there and some good examples of the bandwidth savings you can see. Obviously, there are PCoIP tuning resources available from Teradici and from VMware. I've listed some of those here. And then there are desktop optimization guides as well from VMware, but there's a lot of really good guides out on the net. The first document I reference here is from My Virtual Cloud, and it's an amalgamation of many tuning settings and guidance, and even includes kind of some risk factors for what you can do and what you can tune. And as I mentioned before, I will provide a link to the PCoIP log viewer. So this is the tool that I released that can parse the PCoIP logs and visualize those, but it can also do real-time WMI stats. So you can get the best of both worlds with this tool. And with that, I am done. Thank you very much for watching.